So, is camera working? May I start? Great, so thank you for the introduction, and well, thank you very much for having me here. And well, actually during my PhD student life, well, I always looking forward to getting connected with other researchers in other institutes, and well, actually this is my first time to give a talk here, and so I'm very, very excited here. And well, by the way, I'm gonna attend the summer school in July.
Oh,
so,
okay.
yeah, I'm also very looking forward to it. Today I'm gonna talk about online correlated selection, but well, I heard the audiences would not be that much familiar with the online optimization itself, so I'm gonna briefly introduce the what I call online bipartite part. By the way, I'm going to use Blackboard even though I'm from CS. So this is one of the major inspiration where the OCS comes from. So OCS is online correlated selection. So in online bipartite matching is merely the bipartite matching problem, maximum bipartite matching problem. But here online says that, well, we're given, from the very beginning, we are only given a part of the input. So we only know the vertices on the left side, or say offline vertices. So that's also. And the rest of the input will be coming one by one at each time step. So for here, at this time step, well, a vertex on the right side or online vertex comes, and as well as some edges instance to this online vertex. And what we have to do is, in what online suggests is that we have to make a irrevocable decision here. What I mean by this, in this problem, we have to decide whether we want to match this vertex to one of these offline vertices, and if yes, to which. So say we're gonna match this vertex here. By then, we can move on the next step, and in the next round, say, well, this online vertex comes, and we'll say we match in this way. And in the final round, suppose that only this online vertex can only be matched with this offline vertex. And then here online suggests is that, well, we cannot modify the previous decisions. So this online vertex can only be matched with this offline vertex, but it is already occupied by the previous one. So we have no other option but remaining this offline vertex exposed. So we can see that the size of our solution would be 2, but we can easily see that there exists a perfect matching here, like this. So the size of the offline optimal solution with hindsight would be 3. So this is the solution quality of our this algorithm comes or something. And of course, well, the performance measure of our algorithm would be somehow achieving the minimum over the instances of the solution quality. And this is called competitive ratio. And we'll consider a simple algorithm that whenever an online vertex comes, then we try to match this online vertex to an arbitrary exposed neighbor. Then we can easily see that this would be 1/2 competitive, because well, all maximal matching has the size of at least as a half of the maximum matching. So it will be immediately 1/2 competitive. And actually, for deterministic algorithms, 1/2 competitiveness is the best possible we can do. Therefore, we want to turn our attention to the randomized algorithm. And well, there exists a very well-known randomized algorithm for matching problem, which is called ranking. But I'm not gonna get into that way. But I'm gonna take another let's take a look at another algorithm that I'm gonna present here, what is called two-choice, and this algorithm has gained attention for kind of 3 or 4 years ago, and it is also very simple. So at the very beginning, we're gonna put k sub u for every offline vertices that is given at the very beginning, and when an online vertex arrives, you're gonna choose two offline two neighbors which achieves the minimum k value. And if there are more than two such offline vertices, then we're going to choose arbitrary. And we're going to update, so increase this value by 1. So intuitively speaking, well, k is the number of times that the offline vertex has been selected as a candidate. And we're going to now select uniformly random independently between u1 and u2. And
so you mean probability half, right? So one probability half, which is u1.
That's right. Between these two, we probably have this another half. Okay, so this is the algorithm that we're going to consider today. And well, actually here I omitted some technical details, like what if we only have one such vertices, and what if this u already has been matched? But let's not get into that detail. That is not the main thing that happens.
So what did you write? Select u.
Uniformly random.
Uniformly random.
Between isn't it common things? So sorry, it's quite common from my advisor, but
okay.
And well, I'm not gonna analyze the comparative ratio of this algorithm, but key observation in that analysis is that the expected size of our solution would be exactly the same as the probability that the summation over the probability that every vertex u, every offline vertex u is matched. Well, it's simple because, well, by linearity of expectation, there will be the summation of the this. And we can observe that there will be a list like this. That is because when we consider one offline vertex u, and if it has been chosen as candidate, like this case of u times, and we're gonna choose this. We're gonna try to match this. This offline vertex u. At this time, we're gonna match this with probably 1/2 independently. So the probability that u is still exposed would be bounded from by this much.
Okay.
So we're gonna have this one. And the reason why we have inequality here is because of the omitted technicalities here. So this is the key observation in the analysis, and it turns out that this algorithm would be, so I didn't mention that, well, for the randomized algorithm, we would have this. So this would be the comparative ratio of the randomized algorithm. And this would be simply, so it turns out that the comparative ratio of this algorithm is So we could not get an improvement from the deterministic. But don't be disappointed. Because well, we just got we just observed some clue to get some improvement here. So what I mean by the clue is that what if we have like for every offline vertices, the probability that U is still exposed is at this time where we have this one. But what if we can somehow guarantee that this probability is somehow smaller than this one for some like this or so what if we can guarantee the probability that U is exposed is lesser than the independent choice by a significant factor?
Did you write KU minus 1?
Yeah, here I wrote KU minus 1.
Oh.
Then well we can somehow expect that this value would be increasing, and then well we can expect that this comparative ratio would be better than this independent one. So this is the main topic main question of today's talk. Can we do this? So let's try to take off this part as an independent problem, and so we're gonna like we're given this time step. We're gonna given so at this time step we are given a pair of elements. So here elements will be corresponding to the offline vertices here. So we're gonna take some pair of elements, and what we have to do is we have to output one. So we have to choose one element from each pair. Of course, irrevocably. What we want to guarantee is that for every element U, the probability that U is never chosen is bounded by. So this would be the bound that we can obtain when we choose one element uniformly random independently from each pair. And we want to guarantee this much. So it's the same as this one. So this is the problem that we want to consider today. And actually this is exactly the this is exactly the Fahrbach et al.'s two-way online correlated selection of OCS. So one of their main contribution is that like trying to take off the some sub procedure as an independent problem, and they try to solve this problem instead.
So OCS stand for
Online correlated selection.
Okay. I just read the title of the talk, but maybe you can write.
So they just named it.
Yeah.
And well, at a first glance, you might be wondering how we can improve from the independent choice. Like, so when we choose independently, when we got this bound, but well, how can you do this? But please here note that well, the probability that we are considering is that the probability that U is never chosen from the input. So suppose well we are given like this, something like this. So suppose we are given this, and suppose when we are given this pair, we choose 1. But suppose well when we are given this pair, if we choose U here, then we know for sure that U already has been chosen, so we do not have to choose U here from. So somehow by negatively correlating the choices between the pairs, then we can somehow achieve this. So that is the main idea of the obtaining the good OCS here. Okay, so now let me present Fahrbach et al.'s 1/16 OCS. Here 1/6, so I didn't mention the way gamma OCS, and gamma is parameterized like this. Let me describe this algorithm by example. So suppose we are given these pairs like. So suppose we are given the pairs in this order. So here, this pair arrives first, and then second, then third, fourth, fifth. I'm going to present the algorithm as if it is an offline algorithm, but well, one thing that I want to notice is that well, we can do it in an online manner. But for simplicity, let me present it as an offline algorithm. What we're going to do is, for each pair, we're going to construct a vertex corresponding to that pair. So we're going to construct a graph. So these are vertices, and now we have to make some edges like this. We're going to make an edge in this way. So first, let's consider an element 1. And then we're going to make edges between every consecutive pairs or vertices containing the element 1. What I mean by consecutive is that, so this pair contains 1, and this pair contains 1, but it does not contain 1. So we make this an annotated by 1. And these two are consecutive, so we're gonna do this procedure for every element. So for 2, we have this, and we have this. For 3, we have this, and we have this.
Oh, I see.
And 4, well, we only have this pair, so there's no edges.
So by consecutive, you mean you just make a path for every
pairs that
element.
contains that element.
Okay.
So we skip this one because well, for when we consider element 1, we skip this one because well, only these two pairs contain 1. Then we'll please observe that every vertex will be instant with at most 4 edges. In particular, 2 with the previous vertices and 2 with the following vertices. So we can see this too. But well, still, it still be the case that well, some edges will not appear. And what we're going to do next is that, as every vertex has well, at most 4 edges, instant edges. So we're going to choose one edge, one instant edge for every vertex. We're going to choose one instant edge with probability exactly a quarter. Here, what I mean by exactly a quarter is that, well, so suppose, well, for this vertex, well, O contains, it is instant with 4 edges, so there's nothing wrong. So let's say we choose, for this vertex, let's say this vertex choose this one, this edge. But for example, when we consider this this vertex and say, well, it choose this one. But here you can see that, well, this vertex does not have the edges for this side. But in that case, we simply ignore it. We just do nothing. So we're gonna do it for every vertex like this. Let's say this vertex choose this one, and this vertex choose this one. And let M be the edges. Let M be the edges that are chosen by the both endpoints. And in this example, only this edge can be in M. Because, well, for this edge, it has been chosen by this vertex and this vertex, so we're gonna put it in M. But for any other edges, there's nothing. So it does not satisfy this condition. For this edge, well, it has been chosen by this, but not this. For this edge, this, but not this. So, and when we consider this definition, we can immediately see that M will be a match. In the graph.
In the auxiliary graph? Or
Yeah, in this graph.
yeah, okay.
In this. So we're gonna not consider this part anymore. And well, when we consider the algorithm, here, this definition, well, we have to now choose one element from each pair. So now we have to define what would be the choices. And here, let me write this. For each edge in the matching, so each edge in M, we know for sure that the endpoints, the vertices corresponding to the endpoints will share at least one element by the construction of our auxiliary graph. And then we're gonna negatively correlate the choices between them. What I mean by it is, with probably 1/2, we're gonna choose 1 here, and as 1 already has been chosen, so we're gonna choose 2 here. With the other half probability, we're gonna choose 3 here, but here we're gonna choose 1 here. So we're gonna negatively correlate the choices between these two vertices on the common element. And for the exposed vertices in this auxiliary graph, we're gonna choose uniform random independently one element, like 2 or 4, 1 or 3, and 2 or 3.
So in other words, the choice of the vertex 1, 2 doesn't depend on, just depends on the choice at 1, 3, right?
Yeah.
No randomness.
So it is totally dictated by this rule. You can see in that way, yeah, of course. So it is like, well, one from the front dictates the other counterpart. Okay, so as I mentioned earlier, what we want to show is that the probability that U is never chosen is bounded from above by this. And let me give a very unrigorous proof sketch for it. So let's consider the subgraph of this induced auxiliary graph induced by the vertices containing U. So suppose like so. And let's say, well, the pairs are exactly in this way. And what we know for sure from the construction is that there always exist edges in between honored by U. And now, what if, and let's name these first edges like E1 to EKU minus 1. And what if there exists nice such that in matching? Then if this is in this matching, what we know for sure is that U will be chosen for sure. Because, well, with one half, U will be coming out from here. With the other half, U will be coming out from here. U will always be chosen. So it will not contribute to this probability at all. And notice that the probability that this edge is in matching is exactly the same as this. Because we choose one instant edge with probability exactly a quarter. And we choose this edge in the matching only when the both endpoints are choosing the edge. And by some, it is not as trivial, but it is quite acceptable that these events are somehow negatively correlated. So so this is the true statement. Yeah. It is not as trivial, but well, you can somehow accept that well, they are negatively correlated. Therefore, in order for this algorithm not to choose U at all, we must have not the edges in the matching. And now, then what we can for sure know is that the choices will be, when we only consider this induced subgraph, the choices will be independent. No matter whether this vertex is adjacent with, is matched by some other vertices outside the subgraph, like this. But as I mentioned that M is a matching, so the choices of this negative correlation will not affect the other choices because M is a matching, like this. And well, again, marginally they are all chosen one half, with probably one half. So the probability that condition on no edges are in the matching, the probability that U has never chosen would be this much. And we have to multiply this for it, where gamma is 1 minus 1 over 6. Yep. So this is, of course, it's not rigorous at all, but this is a kind of proof for this. And this is a Fahrbach et al.'s 1 over 16 OCS, and they also obtained some improved OCS with some more adaptation skills and more involved analysis, but I'm not going to get into detail in that way. And well, also Fahrbach et al. Raised some open questions, and one of which is can we somehow obtain a non-trivial multi-way OCS? In this OCS, we only take a pair of elements. But what if we can take 3 or more elements? And can we still obtain a non-trivial OCS?
So with 1/16, so what can you get for the competitive ratio?
For the online bipartite matching, I don't remember correctly, but still we can obtain this much competitive output. Very marginal, but still an improvement by custom, right? Yeah.
Yeah, what's the best competitive ratio for online bipartite matching?
For this version, 1 minus over e, which would be similar to 0.632. It is achievable, and this is the best possible. Well, ranking. But for this unweighted version. Or vertex weighted version, yes, but edge weighted version, no. Okay, so far I was selling the others' result. So now it's time for me to sell my result, our result. So one of the open questions the Fahrbach et al. Raised was, can we obtain a non-trivial multi-way OCS? And we affirmatively answered the question by giving a 3A OCS. Let me increase. And in this time, we are now given, instead of pair, we're given triples. And we have to output 1 element from each triple. And what we want to guarantee is that, well, when we choose 1 element from each triple uniform random independently, then we will immediately obtain this probability. But, well, what we did is we can somehow decrease this. Well, actually, this is not the right form of our paper, but again, well, we can somehow decrease. That's the message that I just wanted to convey. So here is our attempt. So each time step we will be given a triple. And my first attempt was, well, okay, so the OCS itself is quite great and strong. So what if we simply use this OCS in 3-way OCS case? So we simply uniformly random independently choose a pair from triple, and we put it in the OCS, the Fahrbach et al. OCS. And let's consider the output of this OCS as our final output. That was our first attempt, and well, unsurprisingly, it does not give at all any improvement from the previous one. So we need something more than this one. And our next attempt was, then what if we use 2 OCSs like this? So what I mean by it here is that once we get a triple, we're gonna choose a pair uniformly random independently and put it in the OCS. And if the OCS outputs 1 element, and with this element and one that is knocked out from this uniform random choices, we're gonna put it in this OCS again. This was our second attempt, and well, to say conclusion first, well, we got improvement here. Okay, so in order to analyze this OCS, this 3A OCS, okay, well, what we want to show is that probability that U is never chosen is bounded from above by something. And let us say that, well, we are given K U's here. And suppose, well, X number of U's out of K are chosen from this first phase, so X U's. Then, well, K minus X number of U's will be knocked out from the random choices. And suppose, when these OCS are given X number of U's, then suppose, well, Y number of U's are chosen here. And then, well, this OCS will be given K minus X plus Y number of U's. And in this case, in this situation, we want to somehow obtain the how many U's will not be chosen at all. With what probability U will not be chosen. So to write it here, we want to so this part will be this here, and let's say this is OCS1 and this is OCS2. And so when we analyze this probability, then we can indeed obtain this one. And when we consider this part, as we always choose a pair uniformly random independently, this will be corresponding to a simple binomial distribution. K trials, success probably with 2/3, and exactly X number is coming out. And when we consider this last probability, we can see that this is exactly what the Fahrbach et al.'s 2A OCS suggests. Because, well, in the Fahrbach et al.'s 2A OCS, this is what they did. And in this case, well, we are now given K minus X plus Y U's, and the probability that U never chosen from these elements are given. So it is simply the gamma. So let me use gamma here. Yep. So we fit in this probability and this probability. So what remains is this one. This probability. So the probability says, given X number of U's, what would be the probability that exactly Y number of U's will be coming out from the OCS? And actually, this is the major challenge in our analysis. That is because, first, it is not provided from the Fahrbach et al.'s analysis because they only give the probability that U will never, the probability that U is never chosen from the input. But in this case, we want the probability that exactly Y number of U's are chosen from the X. And second, and what is much worse is that we have no closed form formula for it with respect to X and Y.
Okay, can I ask you a question?
Sure.
So here, so in this process, the original 2A OCS process, once some element is chosen, isn't it like we assume that it will never be chosen in the afterward? Or do we allow that it can be actually chosen?
It can be chosen.
Oh, right. So it's not like in the bipartite matching case, where
so that is one that I said earlier that, well, I omitted the technicality here.
Right.
Yeah. And
I
we'll,
see. So here, even if some element is chosen, it can be chosen multiple times. That's why you're talking about
yeah, that's right. It can be
X
chosen.
times out
Yeah,
of
that's
K
right, that's
choice.
right. So it can be chosen multiple times, and here what I omitted is that for the unweighted partition matching case, well, if if an offline vertices has been chosen twice or more, then we simply does not count at all. So that is the way how to interpret that. But in the OCS case, well, an element can be chosen multiple times. So let me back to the context that, well, so much worse challenge is that, well, we have no closed formula for this with respect to only x and y's, because the probability indeed depends on the actual input to this OCS. So our approach, so our goal is like, can we somehow so our goal is to find a safe surrogate P star xy. So what I mean by surrogate here is that, safe surrogate here is that person is bounded from above by So what I mean by a safe surrogate here is that we simply want to replace this part with this P star xy safely. Safely means it still gives an upper bound of that probability. So this actual probability depends on the actual input, so we cannot write it in this way. But can we, is there any, if we can, so can you obtain a safe surrogate distribution that depends on your x and y and gives an upper bound, still upper bound here like this. So that is our goal. And as I mentioned that this probability indeed depends on the actual input, so let's try to fix the input by conditioning on the choices of the uniform random choices, uniform random phase. So when we conditioned on the uniform random phase that U is never chosen, conditioned on UR is that we'll be writing in this way. So as now the input to the first OCS, OCS1 is fixed. So let's say this P is the conditioner probability that in that conditioned input, the probability that exactly Y number of X's or Y number of U's are chosen from the first OCS. So we simply replace this P part here, this orange part in this way. And that's And let me rewrite it. So let's name this as a B of Y. Then we can write it, we can see that it is simply the probability of this function Phi, where Y is chosen from this probability. And please notice that this B is convex. Yeah, convex is always good. So we now want to somehow bound this probability, this one, and to do this, well, we have to now consider or analyze or somehow find any kind of characteristics for this probability P. And this is the probability that exactly y number of views are chosen. So let's consider execution like this. Say x. So we are given x number of views. And in the Fahrbach et al. 2 OCS, we always have edges in between like this when we consider the self-graph induced by the pairs containing U. Okay, so what if we say the edges in between these two pairs are, say, let E be the edges in between these pairs. And what if we have no edges in this in the matching in M? Then, from the previous argument, they are all chosen independently, so Y will follow binomial distribution. And what if now what if we have 1? So suppose, well, this is in the matching M. Then we know for sure that exactly one number U will be coming off from these two pairs. And for the other pairs, they will choose U uniformly random independently. In conclusion, we will follow this. So 2 will be coming out to contribute here, and the rest of the x minus 2 pairs will be choosing U uniform random independently. So let me do it once more. What if 2 edges are in this matching? Then so what this observation suggests is that the outcome probability P here is a weighted sum of these probabilities, where the weights are given by the probability that the number of matching in these edges are exactly 0, 1, 2, blah, blah, blah. And as I mentioned here, as Phi is convex, we have a lemma like this. Also notice that, well, these distributions are all unimodular, symmetric unimodular distributions. What I mean by that is, like, they are all points like a bell shaped. So given two symmetric unimodular distribution P1 and P2, where P2 is flatter than P1, then we would have so the expectation over the pointier distribution is always a lower bound of the expectation of the over the flatter distribution. And well, actually, at the moment when I wrote the paper, I didn't realize, but well, during while I'm preparing this talk, well, I realized that it is nothing but Jensen's inequality. So when we consider P1 as a point distribution and P2 is something like this, then we can easily see that this inequality holds. And we can somehow generalize it. And therefore, our goal is try to somehow find a P star xy, which is flatter than any Py. Because of this. And one immediate candidate would be binomial distribution. And yes, because binomial distribution can be regarded as the weight of this is 1 and weight of these are all 0. Binomial x 1/2. But somehow unsurprisingly we can this only lead to a worse improvement, so it does not give an improvement at all. So we need something pointier than simple binomial distribution, but that is still flatter than any p. And where did I?
You move one more or down. You can move down or
I'm just finding what I wrote. Here. I found it. But here, when we consider this, in the Fahrbach et al.'s algorithm, in the analysis of the Fahrbach et al.'s algorithm, we already proved that none of these edges are in the matching would be, the probability that none of these edges are in the matching would be at most this much. So if we plug this value into here, so here k would be now x, and instead we put this like this, then this gives rise to another distribution. So weight is sum of this and this with weight is this and this. This gives rise to another distribution, and it is indeed pointier than simple binomial distribution, but due to this fact, it is still flatter than any p, because it holds for every possible distribution, real outcome distribution. So using this new distribution as our surrogate here, then we can, and doing some tedious calculations, then we can indeed obtain an improvement. And yeah, that's all on my talk.
Thank you. Any questions?
Yep.
Maybe one natural thing is that why this method does not work for four-way selection because of
I'm so sorry that I forgot something that I have to mention. So one thing is that actually I started with this talk with this unweighted online bipartite problem, but I have to say that Fahrbach et al.'s contribution is not this problem, but the edge-weighted online bipartite matching. And the other thing that I have to mention is that our work is not the only improvement from the Fahrbach et al. The other work from the Fahrbach et al. We have two more independent and concurrent work, which is done by Gao et al. And Huang and Cherica. And actually Gao et al. Improved the two-way OCS itself instead of going in the giving a multi-way OCS, and they indeed obtain a good two-way OCS. And Blanc and Cherica address the same question as ours, and they indeed obtain six-way OCS. And for the edge-weighted online bipartite matching problem, the state of the art is due to the Blanc and Cherica as far as I know.
So for yours, does your work generalize to the edge-weighted version?
Sure.
Uh-huh.
Oh yeah.
I think I'm still interested in his question. Actually, your approach kind of suggests that you can keep splitting up like an n tuple into smaller tuples until you like at some distribution of pairs, and then you keep collecting them together until you have like a kind of tree. Why does this not generalize in this way? Like, is the analogous just horrible or?
Horrible. Yeah, that's the only reason that I can say. Yeah, it's horrible, and then actually I have to mention that Huang and Chorika did some generalization for in that way, for that way. Yeah.
But they also only went to 6, right?
Yeah, so they give some framework for the generalization, but they only give 6 way OCS due to their some technicalities.
They only analyze 6, but
Yeah, so they only obtain 6, as far as I know,
okay.
because of some analytic difficulties.
Okay.
Yeah, so I have 2 questions. Yeah, please.
So do we know some like known upper bounds that you can of the competitive ratio that you can achieve via this n-way OCS?
Some hardness.
Yeah, hardly some.
So
That's-
using 2-way OCS, there exists an upper bound. Yeah. So some upper bounds, but I don't see whether it can be applicable to this online bipartite matching. Compared in terms of the comparative ratio of the online bipartite matching, but there exists some upper bound on the probability that on this probability. So for your question, sorry, I have no idea. Yeah, please.
I was actually probably going to ask a related thing, like if you keep going to higher and higher n-way OCS, how much does this still affect online bipartite matching, or is it just 2-way OCS that actually helps?
Using a multi-way OCS indeed gives an improvement.
Oh.
So that is what our results and Huang and Chorika results provide.
So does it look like it actually substantially improves, or is it like the larger the n gets, the more marginal the improvement becomes?
I have no good answer for that. Sorry. Yeah. So. But of course, that is a good question because finding a good n-way OCS might lead to an optimal matching algorithm. But
If it has to converge somewhere, and like
the
OCS giving 0.5, 0.505.
only
and
for
then
1/16 OCS, and when we use some improved version of the Fahrbach OCS, then we can obtain something better. Yeah. But when we confine ourselves into the 2-way OCS, then of course we cannot achieve 1 minus 3 at all.
But it is fairly realistic that just improving OCS and doing more n-way OCS, you can actually get somewhere close to 0.6. I'm not asking if you can, just like if you believe that this should be possible.
I think that's a very fair question, and that's a plausible way to go.
Interesting.
I wonder, do you think there can be some reasonable physical interpretation of this multi-way OCS? I mean, somehow the analysis reminds me there might be some random walk interpretation of what you're doing. I don't know what I mean, what I'm saying. I'm tempted to try it. It feels like there might be some a physical interpretation of what you're doing.
Sorry, I have no idea of what the physical interpretation of this. Are you meaning that some?
Okay, if you don't have a ready answer, I think it means that it is not known. So.
Well, actually, OCS itself, of course, is used for tackling this edge-weighted online bipartite matching, but it has inspired a lot of other matching-related problems, and so yeah. that's all thing that I can say. Sorry. Yep.
Is it also possible to consider the case when we choose 2 elements for given street instead of selecting one?
2 elements. Well, of course you can come up with that way, but hard to see where we can apply that. That type of OCS.
You see, it's now applicable for bipartite matching.
At least bipartite matching. Of course, well, finding some another applications. Of course, there is a good question for this.
I have one silly question. So they, instead of using, so you have this two-way OCS, and then naive approach to make a three-way OCS might be that you just consider auxiliary graph with the maximum degree 6, right, instead of 4. And then, like, instead of the 1/16, you might have a like
Yeah. So
something smaller. Yeah, but yeah.
Before trying to this one, I tried your version, I guess, and well, I end up with no improvement.
I see. So that's why.
Yep.
It's-
Sorry. So I think you're first. I think you're first. Yeah.
Okay. I was just going to say, so it seems that this two-way OCS, it looks like it's related to the online bipartite matching where every online vertex has degree 2, I guess.
Yep.
OCS itself. Yeah, you're right.
Yeah, so I guess I was just wondering for this, so you have said that there was this bound of 1 minus 1 on E. Does that bound still hold if every online vertex has degree 2?
1 minus 1 over E.
That's
For the ranking.
competitive ratio.
This one.
Yes.
Yeah, you mentioned this as a bound. Just
I
curious,
don't think so. So there's a. Yeah, well, actually, the instance that gives the 1 minus 1 over E uses a lot of degree in the graph. So I don't think that gives some 1 minus 1 over E. Yeah. And well, actually, there also exists some research in the online bipartite matching problem. Yes, I think I can give you one good paper related to that offline, I guess. But yeah, when you
Yes.
So when you say you didn't get an improvement by some method, do you mean you don't get any positive delta in this expression, or do you mean that you don't get a sufficiently large improvement to get a better result for online bipartite matching than
the latter.
The latter, yeah. Okay.
So yeah.
So in your version, what is the value gamma?
Well,
Delta?
so actually, as I mentioned during the talk, well, this is not the right form of our paper, but well, we did something more terrible things like adding 2 parameters here, and well, now we have to put next sign here, and well, this gives so tedious things, and but still gives an improvement for the edge rate on my calculation.
So what's the competitive ratio that you get out of the?
It's quite shameful, but like this or something.
Of course.
And well, the blind empirical gives, they.
Oh, I see.
a lot. I have to mention this.
Alright, so maybe it's a good time to finish the talk.
Yeah.
Okay, let's thank the speaker.